Hello and welcome to this ForceCanvas tutorial. In this video, we'll go over all the features of ForceCanvas using real example sketches so you can get started quickly and easily. It's a bit of a long rambling one, so buckle in. On the home page of ForceCanvas, we can sign up or log in. Once you've logged in, you'll be taken to your dashboard where you'll see some example templates pre-populated. In the dashboard, you can view all of your available canvases. Here, you can toggle between List View or Grid View. You can also create folders and organize your canvases into them using the three-dot menu. To get started, you can either click on one of these templates to open it, or you can create a new canvas. Let's go ahead and open the excavator template. Once we're in the canvas, we can use the beamline tool to start sketching and draw a structure. We're starting with a single beam here. After drawing the geometry, the next step is to add structural supports. We are going to create a simply supported beam with one pin support and one rolling support. After placing the supports, a green overlay appears. This overlay shows us that the beam is now stable and solvable. You need a stable structure before you can solve for the reaction forces. The green overlay tells you the member you have drawn is itself stable. Now let's go ahead and dimension the line and set it to 4 meters. You can use dimensions just like in any normal CAD program. Currently, the line is blue because the sketch is underdefined. We can add more constraints until the sketch is fully defined. Adding a lock constraint to this end of the beam, along with the horizontal and length dimension, we can see the line has turned white. This means the line is now fully defined. Note that the canvas is currently being displayed in dark mode. In light mode, the line color will be black when fully defined because the canvas background is white. Sketches will indicate their definition state with colors. If we have both a vertical and a horizontal constraint on this line, the sketch will turn red because it is overdefined. We are not locked out from adjusting the sketch when geometry is overdefined. For example, we can still change the length of the line, but we will see that it stays red, indicating the geometry may not be in the desired position. So let's go ahead and remove that vertical constraint. If the sketch is red, it may behave in unexpected ways, so we want to keep it either blue, underdefined, or white, fully defined. In ForceCanvas, sketch constraints and structural constraints are not the same thing. The colors of the beams show whether the sketch is underdefined, fully defined, or overdefined. The green overlay shows whether the sketch is structurally stable and solvable. If you are confused about what the colors mean or how the supports work, there is a legend under the gear icon with information to help you. Now that we understand how sketching and adding supports work, we can go ahead and add forces to the canvas. Let's add a force right in the middle of the line with a midpoint constraint snap. The canvas instantly solves for the reaction forces at the supports. We can change the units using the Unit Settings menu in the lower right-hand corner. We'll change the distance unit to feet, the force unit to pounds, and we can also adjust the precision to whatever we need. Let's go back to meters and newtons. Now for a slightly more complex example. ForceCanvas will not only solve determinate structures, which can be solved with static equilibrium equations, but it will also solve indeterminate structures. We'll now draw a structure that is statically indeterminate. First, we will start with a fixed support. As we can see, this horizontal beam is now stable, shown by the green overlay, but the vertical member is not stable. This is because the joint here is set to the default pinned condition, which is free to rotate. This is indicated by the open joint circle. To make this L-frame stable, we need to change this to a fixed joint condition. We can change any joint condition on the canvas by right-clicking it and selecting the presented condition. Now, we've changed this to a fixed joint, shown by the closed circle. This joint will resist rotation, generating a reaction moment internally. Now the L-frame is fully stable. If we add another force, let's make it a horizontal force, We can now see the reaction force and moment at the support. However, this structure is currently still determinate. To make it an indeterminate structure, we can add another support to this end of the vertical member. Indeterminate means it cannot be solved with classic static equilibrium equations. That is one of the powerful features you get with ForceCanvas. We can see that the structure is no longer determinate. The global determinacy indicator at the bottom shows that we are in an indeterminate state. This indicator gives you a sense of the global state of stability for the structures drawn on the canvas. Blue is indeterminate, green is determinate, and red is unstable. Unstable does not mean you can't solve for forces. It is only telling us that somewhere on the canvas there is unstable geometry. To understand if we can solve for forces on specific beam members in the sketch, we need to look at the green overlay, which indicates that a beam itself is stable and can be used to solve. One more thing to point out. This force and this roller support both have a construction control line. This control line is constrained horizontally, and this one is constrained vertically. You can use the sketch constraints and dimensions on the control lines just like any other line geometry. We can adjust these angles by dragging the control lines. We could also use the dimension tool to set a specific angle if we wanted to. As you can see, the reaction forces update here in real time as we drag. This way, we can represent, for example, an angled wall that the beam may be supported by. In some positions, the angle does not provide adequate support, and the global indicator shows us that something on the canvas is unstable. This beam itself has become unstable as it is no longer overlaid by the green beam stability indicator. We can imagine it would swing around the pivot point at this pinned support if it were supported as drawn. That covers the basic examples in ForceCanvas. Let's look at a more advanced one, the excavator sketch. We've already started sketching the excavator. One thing to point out is that we can draw multiple structures that are not connected on the same canvas. Over here we have the excavator sketch, and we are going to add more members to the sketch. Looking at the excavator, the first thing to note is that we have added a reference image. You can add reference images using Image Mode in the toolbar. When we enter Image Mode, we will see an indicator showing that we are in this mode, and our image perimeter will be highlighted. To add images, we can click the plus button to select any image from our File Explorer or Finder. Alternatively, we can simply copy and paste images from the clipboard into the canvas. When we click on an image, a transparency slider will appear above it, and we can then adjust the transparency. This is what we have done with the excavator image here. We started with full opacity and lowered it to see the sketch more clearly. We can also rotate images using a simple rotate handle. To exit image mode, just press the Escape key or click on another tool. Now we will continue sketching. As we can see, this sketch is not fully defined. The geometry is blue. Structurally, the sketch is stable. There is a green overlay on all of the members. This is why we see reaction forces solved at the supports. Now we are going to change this sketch a bit. Once we remove the supports, we can see that the forces are no longer calculated and the structure is no longer stable. Next, we will draw the excavator body represented by a beam line. Here, we are selecting this point and then selecting the line. You can see the possible constraint options appear in the toolbar. We'll add a point-on-line constraint. To add a dimension, we can use the Dimension tool. We can either click it in the toolbar or use the hotkey. If we hover over the tools, we can see which hotkeys to use. D is for Dimension. We'll select the tool and make this line 4 meters long. Now, we'll draw the track frame in. We'll start laying out the sketch roughly, and then add dimensions and constraints. Right now, this is not defined. We can snap a constraint by placing the endpoint of this line near the midpoint of the other. We'll see that it applies the constraint to the midpoint when the mouse is released. Let's go ahead and add some more dimensions. We can use construction lines to help constrain geometry. Construction lines are not used to solve for forces. You're not restricted from adding forces onto a construction line, but these forces will not be included in the calculations. Now we are working to fully define the sketch. Similar to other sketching programs, we can drag geometry and see what is still underdefined. We can see that this geometry here is still not defined, so we will go ahead and add dimensions until it is fully defined. You can double-click on a dimension or a force to edit its value. Now we have a fully defined sketch, but we do not yet have a stable, solvable structure. We want to figure out at what point this excavator is going to tip over with a load in the bucket. We'll add supports to the structure here. As it is now, this is not a stable structure. That's because the joints are set to the default pinned condition and are free to rotate. We'll go ahead and right-click the joints to set them to the fixed condition. The green stability overlay will cascade through the structure as we set the joints to fixed. Now everything is structurally stable and the sketch is fully defined. We are now getting reaction forces at the supports. We want to add one more force to represent the counterweight of the excavator. Let's call it 20 kilonewtons. Now we can see reaction forces in the vertical direction at the supports. This means the excavator is pushing down on both supports, causing completely vertical reaction forces for this simplified support example. Let's take a look at the Hide and Show menu in the toolbar. You can toggle visibility for all of the items on the canvas. If we want to clean up the canvas and make it easier to view, we can turn off elements like beam stability, for example. We can also turn off dimensions, constraints, and even the geometry. Forces and supports can also be hidden, and we can turn off the image if needed. For now, we will leave the image on. With supports visible again, we want to look at one more thing in the Hide and Show menu. There is an option to show the components of the forces. If we toggle this, we can now see both the X and Y reaction force components independently. Currently, we don't have any horizontal forces on this structure, but if we angle this force, for example, the X component at the pin support will be calculated. This sketch is now fully defined and represents a static calculation in this drawn position. However, one of the most powerful features of ForceCanvas is that the sketch is not just static. Forces can be solved while the sketch is underdefined, allowing us to see how the forces change throughout the motion of the mechanism. Over here on the right, we have the constraint panel. This panel shows all the constraints on the canvas. When we hover over a constraint, it will be highlighted on the canvas. One useful feature of the constraint panel is that we can find a constraint and toggle it off instead of deleting it. This lets us experiment with the structure and then toggle the constraint back on to restore it. We've toggled the boom cylinder length dimension off now. After doing so, we can drag the sketch and watch how the forces change. We can also click on individual members and see their isolated forces acting on them. Looking at this top hydraulic cylinder, in the starting position, the force is around 7 kilonewtons. But as we raise up the boom, we can see that this is now a 21 kilonewton load on the top cylinder in this new position. This is really helpful when designing an actuated mechanism. In this example, we could use this to help us size our hydraulic cylinders to handle these forces. Or, for example, we could use it to help us determine a maximum allowable load at the bucket based on predefined hydraulic cylinder sizes. Let's restore that boom cylinder dimensions constraint. We can also just delete a dimension. If we want to delete the dimensions for these two cylinders, we can do that with the delete key on our keyboard. Now, let's adjust the bucket position. One thing to note about the sketches is that they may snap in an unexpected way. Just use the Undo Command button or Ctrl-Z to undo in that case. It can help to drag points that are more closely related to the motion we are trying to actually control to achieve smoother motion. Now we can see that with the arm extended out, the reaction force at the rolling support is decreasing. What would happen if the center of mass of the counterweight was over here? We can see that the reaction force at the rolling support actually flips, meaning we would be tipping the machine. We could use this to help size the counterweight. For example, what if we had a 10 kilonewton counterweight? The excavator will tip over when the bucket load is 10 kilonewtons and the arm is extended out. We can see this because the reaction force is now pointing downwards. This means the support would have to push downwards from above to stop the structure from rotating at the pinned support. This is a quick way to find that we need about a 15 kilonewton counterweight with this excavator design. All right, that about wraps it up. Thanks for watching this tutorial. Hopefully this video helps you get started quickly with the canvas. If you have any questions or feedback, please find our contact page and reach out. With ForceCanvas, structural analysis becomes visual and interactive. Forces update live as we iterate and drag structures. From simple beams to real-world machinery, everything can be done in one canvas. Try it yourself today at ForceCanvas.com.